Yeah.
So I mean, this is basically using Newton's third law, and according to Newton's third law, if there are two objects in a way that one object exerts a force onto the other object, then the other object will exert an equal and opposite force onto the first object. So I told you, I mean, for solving these kind of questions, you have to mark the forces acting on the object, and you just mark the forces acting here. The rod would be experiencing a normal reaction from the ground and friction from the ground. There would be weight acting on the rod. There would be normal reaction acting and friction acting on the rod from the box. By the point of contact, as box exerts a force on to the rod will exert an equal and opposite force onto the box again. So this N2 on the rod must be equal and opposite to the N2 on the box. And this F2 on the rod must be equal and opposite to the F2 onto the box. And there are other forces of the box as well. The weight of the box, the frictional force on the box by the ground, and the normal reaction. But I mean, our main focus is that when there is a situation when two objects are coming in contact with each other, then according to Newton's third law, they will be exerting equal and opposite forces. So these two normal reactions would be equal and opposite to each other as well. These two frictional forces would be equal and opposite to each other as well. So while considering an individual object, of course, when you consider a rod, you will consider the frictional force to be acting upwards, and you will consider the normal reaction to be acting leftwards. Likewise, if you take forces onto the box only, then you will take normal reaction rightwards and frictional force onto the box acting downwards. But when you again the rod and the box together, then you will ignore all of these four forces. So that's our more important point here. So if you say that's our, I'm just talking about force equations. So, and if you're just talking about force equation on a rod, so what would be the horizontal force equation? So you would say that there are only two horizontal forces onto the rod, and they must be, for equilibrium, they must be equal to each other. So F1 must be equal to N2. And when you take the vertical force equation onto the rod, then you would take N1 plus F2, both acting upwards, must be equal to W1 that's acting downwards. Likewise, when you're taking force on box, so your horizontal equation would be N2 must be equal to F3, and your vertical force equation would be F2 plus W2, both are acting down, must be equal to N3, which is acting upwards. But the other thing you need to understand is that you can take an overall force equation as well. That is, you consider the rod and the box together. And when you consider the rod and the box together, then N2 will cancel out with each other and F2 will cancel out with each other. So when we are considering the overall system, then we will ignore these two forces, because the resultant of these four forces would be equal to 0. And even if you're making a horizontal force equation and you put plus N2 and then you put minus N2, so it will definitely cancel out. So you don't need to put these equations. So overall equation, if you're making, so what would be your horizontal overall equation? So you would say horizontal overall equation would be F1 is acting rightwards and F3 is acting leftwards. So these are the two only horizontal forces that you have to consider for the overall system. Likewise, if you're making a vertical, then all of the vertical forces, and in this case, F2 and minus F2 would be ignored. So vertical forces upwards would be N1 plus N3. And that would be equal to W1 plus W2. So, and guys, similarly, I mean, just like that, if you have to you can't make a moment equation because you don't know where exactly N3 acts. But even if you make a moment equation and supposedly examiner says that the box is about to rotate and this is the point where the box acts, I've not marked distances here. but you should know that you can make a moment equation for the entire system as well. But when you make a moment equation for the entire system, then again, all of these forces must be ignored because there is no resultant force because of them, and hence there is no resultant moment because of them as well. So guys, this is also a similar set of examples that you see more often in examination. So resultant of normal reaction and frictional force is called reaction force. So there must be, at the point of contact, if there are two rods resting against each other, so there must be an overall reaction force. And you don't, if you don't know that reaction force, so you can assume that it has a horizontal component, it has a vertical component. But one thing that's noticeable is that both rods will be exerting equal reaction forces onto each other. So the vertical component on one rod, if acting up, would be equal and opposite to the vertical component on the other rod. Likewise, the horizontal component on one rod would be equal and opposite to the horizontal component on the other rod. So considering individual rods, you have to consider these Rx and Ry with their corresponding directions. But if you consider the entire system, then you again ignore all of these four forces acting on the pair of rods. Those guys, I would have been knowing where Rx must be acting, but to be honest, I don't have any idea, any clue where Ry is acting. So I was quite random about this. And if I do mathematical calculations while solving this kind of a question and I get a value for Ry, and if that comes out to be negative, so of course I don't need to redo the entire question again. I would just make that Ry in the opposite direction. That's all what I'm supposed to do. And over here, if you could see a sphere, and we are just making a single plane equation, and you could see a spherical object supporting a rod. So again, if it's in equilibrium, then at the point of contact, they must be exerting equal and opposite forces. So N1, N2 acting up must be equal to N2 acting down on the sphere. F2 acting rightwards on the rod must be equal and opposite to F2 acting leftwards on the rod. And again, I could make separate equations for the rod. I could make separate special equations for the sphere. And in those cases, I would be considering N2 and F2 with their corresponding directions. But if I consider an equation for the entire system, keeping the rod and the sphere together, so in that case, I would again ignore N2 and F2. And you know, this action-reaction pair, Newton's third law, it's everywhere. I mean, even if you consider this point where it's supporting the ground, so there must be an N3 acting downwards and F3 acting leftwards onto the ground. We don't draw it because we will never be making force equation of the ground. But these two are the objects and we can make the force equation, so we have to identify all forces acting on them. Okay. So guys, let's do one question. Let's do one question to help us understand how to go about things. This is the next question on the revision worksheet, June 2011, question 3. Let's start doing it. All right, so there would be a normal reaction acting at point C, and there would be frictional force acting at C as well, towards left. There would be reaction force acting on both the rods at point of contact A. Horizontal component of the reaction force is Rx, and the vertical component is Ry. It's equal and opposite on both the rods. There will be normal reaction on rod B, and there would be a frictional force acting on B as well. Let's consider the moment equation of the entire system about point C. The reason we do that is because there would be no. The reason we do that is because if we consider the moment about C, then the moment of normal reaction at C and friction at C would be equal to 0. And if we consider the entire system, then Rx and Ry would not be part of the equation because they would be cancelling each other out. And your equation would have forces 2W, W, and NB. There would be a zero moment of FB as well because FB is also passing through the point C. So in your moment equation, you'd only have moments of 2W and W, which would be anti-clockwise, and the moment of NB, which would be clockwise. So the moment of 2W would be found by finding its perpendicular distance. That would be 3A cos alpha. The perpendicular distance of W would be 6A cos alpha plus 4A sin alpha. And to find out the perpendicular distance of NB, we can either use Pythagoras theorem, and that would be 5A, or sorry, 10A, or otherwise what we could do is we could find out 6A cos alpha plus 4A sin alpha. So that will give us the perpendicular distance of NB. So once we will simplify this equation, A would cancel out, and we can also find sin alpha and cos alpha, because we have for a right angle triangle we have the perpendicular and the base. We can find hypotenuse using Pythagoras theorem, and hence that will allow us to find out the sin alpha and cos alpha as well. So if we figure out what are the values of sin alpha and cos alpha, and we plug in those values in this equation, so A will cancel out, and by using sin alpha and cos alpha, there will be only one unknown in this equation, which would be NB. And we can simplify this equation to get the value of NB. Next, we will consider the moment of rod AB. Okay, as we do that, of course, Rx and Ry won't be part of the equation, and the only unknowns in the equation would be NB and FB. Since we've already found out NB, so we can solve that equation to get ourselves the value of FB. W and FB will produce an anti-clockwise moment, whereas NB is going to produce a clockwise moment. Distance W from A would be 4A sine alpha. The distance of FB from A would be 8A cos alpha, and the distance of NB from A would be 8A sine alpha. this equation, we can substitute the value of NP, and hence there will be only one unknown left in the equation, that is FP, and we can rearrange that equation to get ourselves the value of FP as well. If you consider the resultant horizontal force of the entire system, again the reaction forces between the two rods would be cancelled out, and there would be only two forces left. One is the frictional force acting on the rod AB and the frictional force acting on the rod AC. And as these two forces are acting in the opposite direction, so therefore FP must be equal to FC. Finally, to find out the normal reaction at point C, we will consider the vertical forces of the entire system. That way, we will only have NP and NC in our equation. If we've already found out the value of NP, if we plug in that value, we will be able to find out the normal reaction at C. Now we can apply F is less than equal to mu n at both points B and C. As we're getting two range of values of mu, one is mu is greater than or equal to 0.692 and the other one is greater than or equal to 0.367. So we will pick mu to be greater than or equal to 0.692, which will ensure that it would be greater than 0.367 as well. and hence there would be equilibrium at both the points A and C.